everyone's paying attention when I say anime again. So. All right. Hello. Hello. All right. 6.4.
Say it in German.
Donkey shake.
No, not donkey shake.
Guten Tag.
Isn't that like it?
That's good morning.
Yeah. Good morning.
No,
Guten Morgen.
Yeah.
Guten Morgen.
Yeah.
Dankeschön. Is that what it is? Yeah.
That's thank you.
Yeah, isn't that thank you? I was like, Dankas.
Danke. Yeah. I don't know.
Anyways.
So we had a couple.
America.
America. Yeah. Okay. Anyway. Okay. Volume of solids. So we've already been doing a bunch of solids, right? Revolutions, whatever the F that under it, right? And then we rotate that F, and then we get a volume out of that F, right? So it's an area of a cross section.
What?
Anyway, the area of a cross section times the thickness would be the area of the whole thing. The thickness is going to be my delta x, right? And the area of the cross section is whatever shape that is, right? Here's the formula. From B to A, as however big something is, right? Using slicing to verify that the volume of a right circular cone having a radius r and a height of h is going to be this. Cone. A cone. What would a cross section of a cone be? It'd be a circle, right? Yeah. Yeah. So a cone, if I slice it up and down perpendicular to it, that would make it's parabolas. Makes parabolas.
Yeah, you're right. Because it's like boom, boom. How? I can't recreate the notes. Boom, boom.
Here's your S term.
I actually have a bunch of these things, and they're all cut.
That you never use? Is it behind the food?
It's funny, when I was actually making the notes, I was like, oh hey, I should probably grab those things.
You never grab it?
Yeah. I mainly use it for geometry. Ah, here they are.
Blocks.
There's my cone. Cone, right? Different slicing of cones.
Is it like, well,
Pitch
you
it
get
right
a
out.
cone,
No.
you get a cone.
Okay, there we go. All right, so there's a cone, and he's got the one that's actually slicing it perpendicular. And so if you slice it at a diagonal, you get a what? What shape you get? What shape is the cross section of that one?
It's like an oval.
Which is a mathematical term?
Oh, an
Ellipse. There we go. All right, so now that thing right there. Okay, look at the end. Look at the end. Yeah, okay. What's a cross section if it is parallel to the bottom? Yes. Yeah, it's going to be a circle. So the cross section of it, if you do it parallel to the bottom, it's going to be a circle. All right? Now, what is the cross section of that one right there? That's your parabola, right?
Purple.
Yes. So if it's not going through the very peak of it, it's going to be a parabola. If it goes to the very peak of it, at the very tip, that's going to be a triangle. Okay? So if you guys want to pass those around and see, you can. All right, so using a slicing to verify that the volume of a right circular cone having a radius of r and a height of h, okay, should be this. Okay, so let's start off by, let's verify what we're talking about. So if we're doing this, okay, so let's say, here's my cone. And a slice of this right here would be what? There's my circle, right? A slice is going to be the circle. So in this case, since we don't know the function of it, I know that from here to here is going to be x, right? Right? And for the whole thing, that's supposed to be what? That's my h, right? Because I'm verifying this formula over here. Okay, this right here, from here straight up and down would be my what? That would be my r, right? This is going to be my r value here, or in the case of this function would be f of x, right? Okay, that would be my f of x. And on this case right here, from here to here, would be, we're going to call that one a capital R, because it's actually asking me to use those terms. So we're going to do this by setting up a proportion for this. I know that, let's say, r over x should be proportional to what?
Big R over H.
Yes?
Yeah.
Okay. Yeah? Okay. So now that I have those proportions, okay, do me a favor, don't keep dropping those because they do break. I've already had a couple break. So it should look like this. So same thing, but this one is actually a lot better drawing. Right? So what area am I dealing with my cross section? What shape? What shape is the cross section?
Circle.
Circle. Very good. How do I find the area of the circle?
Pi R squared.
Okay, so area of the circle, pi r squared, right? Okay. Yeah. Okay. So now I don't want that. I want this. So what I've did with this information right here. Okay, we can go through and do cross products to be able to get r by itself. So multiply both sides by r. So I should get this right here. So now from there, I'm trying to verify that other thing. So let's replace r with this. What I just underlined right here. If I replace that, that's going to turn into area is equal to pi. My r is going to be all of this, capital R x over h all squared, right? Yes?
Yes.
Okay, good. All right, so keep going. So it's going to be area is going to be pi r squared x squared over h squared. Okay, so we're going and we're trying to verify this. So if we go back, we're verifying this using this right here. Okay, slicing. So area of the cross section times the thickness of the slice. And the thickness of the slice in this case would be what? So we have the area of the cross section, right? Say yes. Okay, since I have the area of the cross section, And so that's going to be a dx, right? Yes, dx. So it's going to be delta x. So times this is going to give me the whole thing. So it's going to be all of this pi r squared x squared over h squared, and that's delta x because that's going to be the thickness, right? Of there, right? Integration of that. So I don't actually have any real bounds on this yet. I know that it's just going to be some formula for this. Okay? So now, if I'm going to integrate this in terms of what? X. So I'm now going to come up with, in terms of x, that's going to be 1/3, right? 1/3, because I add 1, right? Pi r squared x to the 3 all over h squared. And so for this whole thing, how would I start this one? Look at the cone. So if I were to add some bounds on this, where would my bounds go?
0 to h.
0 to what?
No, wait, no.
0, say it.
0 to h.
Okay, good. 0 to h. 0 to h. So now I can get some bounds on this, and this is going to be for every single one that I plug in, right? Okay, so I'm going to next, I think I need next page on this one. Yeah. Insert page blank after current. So again, we had from 0 to h. Actually, no. Let's go with the other one. So 1/3 r squared x cubed over h 3, right? I'm missing a pi, right? Oh, you're right. H squared. Okay. And pi and 3. There we go. And that's from 0 to h. So let's go ahead, plug it in there for the bottom. So what's going to happen at the bottom right here? So it's going to be, so if I plug in h, it's going to be pi r squared, right? And that's going to give me what? H to the 3rd over h squared. Yes? Minus pi r squared 0 to the 3rd over h squared. What's going to happen to my h's now? What's going to happen to my h's over here on the left? Yeah, divide. What's going to happen? Am I going to cancel out? Yeah, I'm going to cancel out 2 of them, right? So now I'm left with 1/3 pi r squared h minus 0, isn't it? And that's equal to my volume formula. So the whole formula for the volume actually came from doing integration using slicing of this. I actually just thought it was neat, but, you know.
What was integration invented? Wasn't that in the 1700s?
Yes.
They didn't have the volume of the cone until the 1700s.
You have the
think it was a verification of the volume of a cone, mathematically. But anyway, but still. All right. Okay. Slicing. Is this the one on? Yeah, this is another one. Solid base has circular. A solid has a circular base, a radius 3. Okay, so the base of this is supposed to be. Okay, circular base, radius 3. So at the base, what's it across?
6.
Okay, 6 all the way across, right? That would refer to the diameter of whatever that circle is right there, right?
Yeah.
Okay, good. Find the volume V of the solid if every plane cross-section that is perpendicular to a fixed diameter is an equilateral triangle. Here, I'll start with this, because as you see it like this,
Oh, okay.
Gel and mold. Okay. All right. So does this make more sense now? Now that we see place center, circular base, so that means that I'm going to have from there, whatever the values I have, since this is supposed to be a circle, right? It's supposed to be a circle, and the radius is supposed to be
6.
3.
Radius.
Radius is 3, right? Okay. So we come up with the formula right here. Equation of a circle, right? Okay, so I'm going to take that one, and I'm going to go back over here. So my equation of the circle was x squared plus y squared equals my radius squared, which is 3 squared, like this. And I get x squared plus y squared equals 9. So that's a start right there, right? And we know, okay, find the volume of a solid if every plane cross-section that is a perpendicular to a fixed diameter is equilateral triangle. Equilateral triangle. Okay, so if it's an equilateral triangle, what do I know? So it should look like this, right? Equilateral triangle. So in the case, I'm going to use the same variables that they had. So we said that this is y, that's y. So being an equilateral triangle, what do I know about the sides?
Side should all equals.
They should all be the same. So what is diagonals over here going to be? 2y. It's going to be 2y, right?
Yeah.
And this is also 2y. So what type of triangle is this going to end up being? So if it's equilateral, what's the... I know, no. But think about this. What is every angle supposed to be? 60. But if I slice it so I know what my h value is here, right?
30, 60, 90.
It's going to be a 30, 60, 90, isn't it?
Yeah.
So being a 30, 60, 90, this is 2 times y. This is y. What is my h going to be equal to?
2y squared minus y squared.
You could use Pythagorean Theorem on this one, if you guys don't know it.
Oh,
It is a special right. It's a special right triangle. So if you don't know it, please do the math right now. Okay, use Pythagorean Theorem to find whatever the h value is supposed to be. There it is. I need you guys to actually map this. Because isolating and finding your variable, you're not finding it in the calculator. Turn down for what? There you go.
So we're trying to find h.
Yeah, what would h be? I'm sorry. H would be what? because it should be, let's see, if it's going to be 2 equals y squared, right? Plus, right? So I want to find out what my h is supposed to be, right? Okay, so let's go ahead. So that's going to become, let's see, it's going to be h squared is equal to 4y squared minus y squared, right?
Yeah.
So that's going to be h is equal to the square root of 3y squared. What's going to happen to that y?
It's gonna become this.
It's going to come out, right? So h is equal to y square root of 3, isn't it? You guys remember the special right triangle now?
Yeah, I do.
Now you do? Okay, y
Hey, I said that.
square root of 3. I couldn't speak up.
I
Okay,
doubted myself. Thank you.
okay. Good job. Okay, so we get that. So we have a value there. So now, perpendicular fixed. Okay, so find the volume V, every solid plane cross. Okay, so now, can we find the area of that? So what shape is that? Triangle, so let's go with that. So area is equal to 1/2. So it's going to be 2y
times y rad 3.
Yes? Okay. So that's going to be the area of the cross section, right? Area of the cross section. So this is going to give me area should equal y squared rad 3.
Yes.
And so that's that part, right? Area of the cross section. So now what's the part that comes next?
Delta y.
So this is going to be delta y, isn't it?
Yeah.
So we're going to delta y this one. So delta y means I'm going to take an integration. Okay? Integration of, right here, y squared root 3 times delta y and from where to where?
Is it 0 to 2y or 0 to h because we're in y?
In this case right here, if you go back to the drawing, y was given for this one right here.
Okay, yeah, then it'd be 2y.
So it would be 0 to what?
0 to y. 0 to 3.
It should be 0 to 3. Okay, it should be 0 to 3 there. Okay, we should come up with 0 to 3. Did I lose it? No, there it is. Okay, so right here, yeah, do I need another page? Yeah, I do. All right, insert page after. Okay, so, and this was, what do we say this was? Y squared?
Yeah, y squared rad 3.
And delta y. So as I take my integration of this, it's going to come out to be y3 over 3 rad 3 so we're going to come up with 27 over 3, which is 9 rad 3 minus 0. And so for this one right here, it's going to come up with just 9 rad 3. So sometimes these are easier, sometimes they're not. Okay, the application I think is actually really good. The theoretical, I think, is pretty good too, where we're just talking about like what it could be, what it should be. And I'm making sure I got that one. Oh crap, I did not. Someone was right. I was wrong. Who was the one that actually got it right? Who's the one that said I need it in terms of y, or in terms of x? Because this is my x value right here for the cross section. Yeah, because it's going three-dimensional, I was thinking this as going right here, calling out the y, but that one's supposed to be up for this. So I was wrong. I was wrong. Someone said that. Who was that? Was it Andrew?
Did I say like, is it going up?
Do I need it x's or y's?
That was me.
There we go.
Okay.
Okay, so yes. Okay, you were right. So let's go back. I'm going to clean this up. So everything is, we had everything right. So we know that it was plugging back in. So I have, so now I came up with, what did I come up with? Right here, it should be rad 3. So I replaced y squared with, okay, with what I had. So this is going to be rad 3 y squared, right?
Yeah.
That's what we came up with. So rad 3 y squared, so I'm going to replace that with 9 minus x squared. So I'm replacing it using Pythagorean right here. So yes, you were right. I need it in terms of x. That's where I messed up because my bounds were 0 to 3 from there to there. So it's going to be my, let's see, put rad 3 out front of 9 minus x squared, and that's my dx. So, I feel really bad. Thought I had this too. I was like, man, God. Okay, so now let's go ahead and do this one right here. So it's going to be 9x minus x cubed over 3 from 0 to 3. So 27 minus 27 over 9, which is 9, minus 0. So we come up with 18 rad 3. Yes, 18 rad 3. All right. I think that was the other one I was going to do. Pyramid, square base. How would I set up this one if it is a pyramid with square base? What is my area I'm looking for? Say a square.
Square.
Okay, and that would be the same thing. Pyramid, kind of like we do with the cone, right?
Squares.
Yeah, so now this one's going to be a square. So cross section here is square. And so it would be just like the first example that I did. So we have to go through and set it up, you know, same way. Let's see. Yeah, here it is, setting it up the exact same way. And slicing right here, find the region R, graphs this, bounded by these two right here. Okay, same thing, when you come up to the graph, you could actually see that each one is going to be a square. So when we figure out where they're bounded by, we could figure out that those two actually equal at 0 and at 4. So when I set them equal, I come up with that. So this whole thing comes from graphing it, but we don't have the 3D graphing on our calculator. And then each little piece in between is going to be a square. Find the area of a square, multiply that by my delta x, my thickness of whatever shape that would be for my cross section. So did I bore everyone to death?
No.
So it's just a different way of doing this. It's another way. So if you guys like the, you know, the other methods, it's fine. I think there's, is this the arc length next one? Nope. Okay, that's it. Arc length is on the next one. So yeah, tomorrow we got arc length. Oh no, tomorrow's Wednesday, my dudes. Like